Kutoni, Fiboa, Yua Ishai, Peter Rindal, and Peter Shaw. And so the setting, like first to explain the title briefly, is secure multi-party computation. So we want to allow 2 or more parties to securely evaluate public functions on their inputs, such that the parties learn the function output and nothing more. And this is something we know how to do since a long time ago, and we even know how to do succinctly with fully homomorphic encryption, but still a question is about concrete efficiency. So this talk today will be mostly about concrete efficiency. And one approach towards this is to push all the expensive cryptographic parts to an input-independent preprocessing phase, where the parties generate long correlated strings that can then be used to implement a very efficient online phase. And so this has lots of great properties. The online phase is very lightweight, information theoretic. You can get security against dishonest majority and against parties behaving maliciously. But the problem with this approach is still the preprocessing phase, which is expensive, because typically the online phase requires a large amount of correlated randomness. And in order to produce that, typical protocols require communication and storage at least linear in the amount of correlated randomness needed. And so in order to improve this, in order to get sublinearity for secure communication, what we do is use the simplest thing we can do is use a pseudorandom generator. And so what we can use here in order to make it more efficient is a pseudorandom correlation generator. So pseudorandom correlation generator allows to extend short correlated seeds into long correlated pseudorandom strings. And to be a bit more formal, if like a pseudorandom correlation generator, it consists of a gen algorithm and expand algorithm, and the gen algorithm sets up 2 seeds that are correlated, and then the parties can locally expand those seeds K0 and K1 to get long strings. And of course we want correctness, so that these are correlated in whatever way we want them to be correlated. And like what is a bit more difficult to get is how to define security. So as I said, we want to use that for secure computation. So maybe the most straightforward or the most desirable notion would be to get a simulation-based security notion, but this turns out to be impossible. So we settle for, or like the definition settles for next best thing, which is an indistinguishable-based security notion. So the requirement is that a party itself from the short seed cannot learn anything more about the other party's output than it can trivially just by knowing that the 2 are in a correlated. And of course, now the question is this still useful? And otherwise I wouldn't be showing it here, but it turns out, yes, you can even use it as a direct plugin for a wide number of protocols. And namely all protocols that allow kind of to replace the ideal functionality for preprocessing by a corruptible functionality that allows the adversary to choose its own randomness and then sample the honest party's randomness conditioned on the adversarial chosen randomness. And a lot of natural MPC protocols are already secured in this setting. So for all this, we can use it as a plugin replacement. And now just to put
Lisa,
things together. Yes, sorry.
Lisa, this is Vinod. Quick question. So the security experiment is not sort of polynomial time, right? In your previous slide. The security experiment needs to either sample R1 or it needs to sample R1 conditioned on R0. Is that right, or am I missing something?
So the security experiment, so like what we want is it's distinguishable whether you just take R1 to be the expanded output, right, or you sample R1 conditioned on being in correlation with R0. So we need, we consider correlations where you can do that.
Okay, that you can do there where you can sample this R1 condition on R0 and polynomial time.
Yes, yes, exactly.
Okay, got it. Okay, thank you.
Okay, thanks for the
There's
question.
just a question in the Q&A, which is closely related to what Vinod was asking, which is just what this notation means. So I guess this notation means like
Yes.
R1 conditioned on this correlation between
Yes.
R0 and R1.
Yes,
Okay.
yes. And
Great.
like for correlations that we want to like consider, like so generally we will consider additive correlations where you can where you can always do this by just sampling accordingly. Okay, thank you. So is there another question?
Yes, so the question is, what if there's a bijection between R0 and R1, but neither direction is efficiently computable?
Okay, so like we care only about correlations where this is efficiently computable. So like really correlations where you have like you can efficiently sample. So like for later you will see for the applications, the correlations will be something like additive secret sharing of a product or something like that, where you don't have this problem. Okay, sorry, I should have been more precise about that. Thanks. I hope this.
One last clarification once we repeat it. So assume that expand is just a standard PRG. So the keys are chosen uniformly and the output is pseudo-random. By conditional probability, you mean it is a uniformly random string or a uniformly random pseudo-random string in the image of expand?
So like if you mean what if we would just instantiate with a PRG? Then this wouldn't say anything, or this would just say, okay, like if I just instantiate with a PRG, then I know the other party's output because I know that the other party's output is my output because the correlation would be the equality.
No, but if you have some other weaker correlation, so R1 doesn't have to be in the image of expand, correct?
Oh, so no, like from any, it's indistinguishable from any R1, not just from an R1 that is in the image from expand. So it's like really, it's random. So you have some pseudo-randomness there. So it's indistinguishable, like computationally indistinguishable from any other value that would be correlated to R0, but it does not have to be in expand for any key K1.
Mm-hmm. So this relation is given to you separate. It's not a relation that, so there is a relation between R0 and R1, which is defined implicitly by the two expand functions and the execution of Gen1.
So the correlation, we have a correlation, like I should have explained this differently. The correlation is given ahead of time, and then you find a PCG for that correlation. So the correlation is fixed, and then you find a PCG for that correlation. And for that correlation, you want the security requirement to hold. So like you can replace this correlation by something that you can get by the PCG because the output of the PCG is indistinguishable from something that is just sampled according to this correlation, even from my view. Does this make sense?
Thanks. Yeah. Okay. Perfect.
Okay, great. Thanks. Okay, thanks for the questions. I hope the definition is clear now. It's actually very important. So thank you. And now that we have it, so yeah, we will always consider like a fixed correlation, and later I will be more explicit about this. But like once we have a PCG for this correlation we care about, we can now use this to get more efficient silent preprocessing, because we can now have a setup with sublinear communication and storage, like storage for sure, because the parties just have to store the short seed, like we can also hope to get away with much less communication. And then the preprocessing itself will be completely silent. So once the seed is set up, there's no more communication between the parties required. So what you get is secure MPC with silent preprocessing, in particular sublinear communication and storage. And this is very nice also for also for malicious security, because now to make it maliciously secure, you only have to make the setup phase secure. So even if you have like a small overhead, the expansion and the computational time is almost not affected by that. So you get malicious security. This is also something we show in this line of work at very little extra cost. And now this is maybe something also to make the correlations a bit more clear. If we have like a fixed correlation, and here by correlation is an additive correlation, so I want to have R0 and R1 such that R0 plus R1 are equal to f of x for some x that is chosen uniformly in random, and f is the correlation we care about. And now here you can also see if like the adversary provides R1, we can just sample R0 as f of x minus R1 and have something that satisfies the correlation. And we will always, like, I will just talk about additive correlations. And for feasibility, this is also, I mean, like a lot of this talks in this week were actually about just feasibility. And here, like, we will have feasibility after the slide, and then the rest of the talk will be about concrete efficiency. So you can get PCG for this correlation by if you have a PRG and a suitable homomorphic secret sharing scheme. And homomorphic secret sharing scheme is already something we saw in Ayush's talk on Tuesday. It's basically, just as a reminder, it's the secret sharing analog of fully homomorphic encryption. So that allows, you have secret shares and you can do homomorphic computations on the shares. And here, the difference here is that we really need homomorphic secret sharing where the reconstruction is additive. So how can we use this if we have that? Now we can, instead of sampling X, we can sample a short seed of X and share this with the homomorphic secret sharing scheme between the two parties. And then using the homomorphic secret sharing scheme, we can evaluate first the PRG and then the function f that we care about, the correlation we care about on the shares. And then by correctness of the homomorphic secret sharing scheme, we will have that R0 plus R1 equals f of PRG of x, f of PRG of the seed of x, so f of x. And because the seed will be much shorter than x, and homomorphic secret sharing, we have succinctness of the shares, this will also like actually give us something interesting, so something that is compressing. And yeah, so this gives us already a feasibility, and this is kind of also what makes this landscape, at least like the orange and the yellow part. So building on homomorphic secret sharing techniques, you can basically get something for general additive correlations. And you can also, like on the other side, this you can get from one-way functions, you can get interesting things. You can get truth table correlations. You can get linear correlations for multiple, like in a multi-party case. This is something already from like 20 years ago, kind of the start of PCGs. And yeah, and as you can see, there's a white missing. I think there was a question. Should I?
The question is just what LWE plus means.
Oh, like LWE just with circular security, like the circular security requirement that you don't have to know a priori like the depth of the circuit. And yes, and there's like a big blank here, and this blank here is, I have to click again. So this is actually what I want to talk about today, is that it turns out that Lapland, so the learning parity with noise assumption, turns out to be very useful to construct concretely efficient PCGs. So as you can see here, this is like a lot of green things, vector, oblivious linear evaluation, Oblivious transfer, Oblivious linear evaluation, something we showed like in a very recent work from a variant of ring learning parity with noise. And yes, so OT and OLE, this is the two things I also want to talk about today. And yes, I think I'll continue with this, and about some things I'll talk more later. And as we have...
Alisa, this is Hotek. Just a quick question.
Yes.
In your previous slide, when you wrote f of capital X, is capital X some sort of input, or should I think of it as a random variable from some distribution?
I think of it as an input for that. So like you sample it, like you can, I mean, you sample it uniformly. So if you set up the correlation, you will sample this. So
but X is not the,
it's a random variable, but
okay.
but here you can think of like I want to instantiate it, so I sample a random X, and then I plug it into F, or like, and then in the PCG I sample instead of seed of X and then use the PRG to get the X.
Okay. So X won't be related to like inputs to MPC or that kind of inputs.
So this is all random. So this will all randomness because like in the preprocessing phase, what you want to generate is just like completely, like you just need pseudo-random correlations in the end. So this will not have nothing to do with the actual inputs for the MPC. This is just really something that you want to be random.
Okay, thank you.
Okay, thanks for the question. Okay, great. And so yes, we have seen this this week. I've seen a lot of like more learning with errors, or like yes, I think no learning parity with noise. And so what's the difference between the two? So first of all, learning parity with noise, as the name says, was originally, or like does consider correlations, or does consider is over F2, but actually here we will consider also arithmetic versions of that. So like you can think of P being 2 being larger. We will see both in this talk. And so the difference that makes LPN for the setting interesting, and the difference that we have is really how the error is distributed. And in LWE, we have error with small infinity norm. And for learning parity with noise, we have errors with small Hamming weight. So basically you can view the error as a sparse vector, and this is where like the magic comes from. And yes, so we have seen that from learning with errors, like you can do a lot of a lot of things, and a lot of great things like polymorphic encryption. Not as we've seen like the last days, not all yet that we want to do. So I was still outside, but like already a lot of things. And how does this work look for learning parity with noise? So actually what we get is much smaller. So if we just considered learning parity with noise, we can do basic things like PRG, secret key encryption, one-way functions, but like really not a lot. And if we go to low noise, so we have sparse errors with just few entries, like less than square root of n, then we can do more. We can do public key encryption, OT, but it's still like a lot less expressive than LWE. But what we will get here is actually like concrete efficiency, and this is like a setting where really LPN gives something much more efficient than LWE, as you will see. And what I will show in this talk is how you can get PCG for OT, actually for learning parity with noise with arbitrary noise rate, and PCGs for Oblivious linear evaluation if you go to the low noise rate regime. And this is something this is the two things I want to talk about today. And yes. So why is learning parity with noise so great? Or like first, okay, basically, as you've seen before, like what we want for making PCGs work is a pseudorandom generator. And how do we get a pseudorandom generator from learning parity with noise? Well, like one way is just you can just view the seed is just the secret and the error positions of the sparse vector that can then extend. And this is already something, and this also gives you something, but this is limited to quadratic stretch, because if you go beyond quadratic stretch, you can just guess enough noise-free coordinates and then trivially solve by Gaussian elimination. So if we want to go further, what we will do is go to the dual LPN assumption, where like if you consider the matrix that's a parity check matrix, if you view it as like a code, to the generator matrix G, then those two assumptions are equivalent, and now we can have arbitrary polynomial stretch. And the reason is just because now we don't have to also give the secret as a seed. So the secret can be larger now, but that doesn't, like, now we don't have limited stretch. So this is what we will use, and the two assumptions can be shown to be equivalent. And why does this? Why is this a perfect match for pseudorandom correlation generators? So there's like two reasons, and the important reason is that that's also what's the difference to learning with errors, is that the sparse vector can be distributed via compressed secret shares. So I can, in the next slide, I will explain what it means in more detail, but you can find like a compressed way to distribute seeds that you can then extend to get an additive secret sharing of a sparse vector. And the second thing is that, and this is basically what will give us the compression. And the second thing is this, if you see, this is just a matrix multiplication. So this is completely like the PRG evaluation, except for like transforming error positions in something longer, is completely linear. So this has like nice homomorphic properties. So basically we can just do linear operations on additive secret shares. So like the simplest homomorphic secret sharing scheme you can think of in some sense. And yeah, why can you distribute sparse vectors efficiently? So for this, we won't actually not like I will like explain how to distribute a unit vector efficiently. And if you distribute a unit vector efficiently, then you can distribute a sparse vector efficiently by just like distributing many unit vectors and add up the outcome. And we will not view it as a unit vector, but we will view it as a point function. So point function is something that came up yesterday in Venkata's talk briefly. And what a point function does is just a function that's non-zero just at one point. And it's like we view it in a different setting here. So the output space will correspond to the length of the vector. So if you have like a vector of length n, you can view this like a unit vector of length n. You can view this as the output, like the complete output of a point function that is just non-zero at this one point. And like now distributed point function is just a compressed version to like give out K0 and K1 to two parties that they can extend to. And like here extending meaning evaluating at point 1, 2, 3, alpha and n. And then if you add it up, you get 0 everywhere except for this point y. And like the properties of distributed point functions is that the parties don't learn what alpha is, and the parties also don't learn what y is. So like other than the picture where the first party could see where alpha is, this is not the case. And this is nice because like why so we have efficient constructions of those distributed point functions, so compressing constructions of sparse vectors from one-way functions. And what you also need for PCGs, you don't only care about that you have a PCG, you also need to set up the seed efficiently. And for those constructions by Derner and Shelat, there actually exists efficient distributed setup of the seeds. And I think there was a question.
Yeah, so there's just a quick question from Mark, which is what the quantifier on y is.
What is, sorry?
So how is y quantified? Like,
so y, like later you will see what y is, like y will later be chosen by one of the parties basically. But so you will see how this y is chosen later. I think like later it's easier to explain what is good for. And so it's just a fixed y, so you can view the point function as indexed by alpha and y. So it's a bit sloppy. I didn't write it this way. Maybe this answers the question also. And now that you've seen this, actually, and now we have a distributed point function, so we can compress a unit vector between two parties. And as we can compress a unit vector, as I said, we can compress like any sparse vector. And this is actually like those two slides are actually all you need to know, like all you need, you kind of already now should know how to do like a PCG from learning parity with noise. This is like really the main ingredients, but now I want to take the rest of the talk to give a bit more details. How do we get a PCG for Oblivious transfer from learning parity with noise? Just basically with these techniques, we can do a bit something smarter and get better efficiency, but this is already enough. And later in the end, like I want to spend a few minutes to talk how can we get OEs from like a kind of bit different assumption, but efficiently. And so Oblivious transfer, like just very briefly allows Bob to obliviously send a message to Alice. So does that, like, Alice just learns one of the messages and Bob doesn't learn which message Alice chose to learn. And this actually, like by Kilian, we know that this implies a secure multi-party computation. And not only this, with the, for example, the GMW protocol, we can get very, very efficient secure computation if we have lots of random OTs. So basically in the pre-processing phase, set up many of these. And this is great. And the only problem that we have is that OT is expensive. It's a public key primitive, which are generally expensive. And to overcome this, what like originally Beaver and later Ishai et al. Worked on was so-called OT extension. And the idea of OT extension is, okay, like there is a result that I cannot get out without OT completely, but what I can do is I can just need black box access to like a few OTs, and then the rest I can do with cheap symmetric crypto. And so I get something like this. Basically solves the computational efficiency kind of point, but the problem is, like, we still have a lot of communication. So this is of course necessary if I care about chosen OTs, but in the context of secure computation, I just care about random OTs. So in order to do random OTs, I can actually use the pseudorandom correlation generators, as I saw before, to get what we call silent OT extension, where, like, additional to the computational savings, you have saving in terms of storage and communication. And so yes, I want to spend a few words on like what OT extension protocols are known. So like, as I said, the first one was by Beaver, like 2-round, but not practically efficient. And then later there was a number of protocols which are concretely efficient, but with the downside that they require actually, like, first, or with the downside, like, with the downside that they require still a lot of communication. So communication is still, like, even in the order of 70 bits, even if you only care about the single bit OT. So for single bit OT, you still needed to communicate like a lot of bits. And this is something, if you use PCGs, you can actually bring down, so asymptotically to 0 bits, but with concrete implementation, even concretely, you get something like 0.1 bits, so almost a factor of 1,000 improvement. And another interesting, so this is just kind of the advertisement slide why you should continue listening for the rest of the talk. Another interesting result of this line of work is that it gives you the first efficient 2-round OT extension. And so in some sense, there was a law bound by Garg et al. That from symmetric key primitives, you cannot get in a black box way 2-round OT extension. Of course, our construction is not black box, but it has, like, as I said, in some sense, it lives in the symmetric, it can live in the symmetric key vault. So yes, it's also something like I find interesting, and it has a lot of practical applications. So directly, big improvement to semi-honest 2-party computation, improvements on private set intersection, malicious MPC, and also applications to non-interactive secure computation. And yeah, so the rest, I want to explain how this is done now that I said, well, like what you can, what's the result is. And so, like, I showed you the Oblivious transfer correlation. It's like the way I wrote it, it's not very linear. So the first step is to rewrite it as something that looks more linear, and then it though is like therefore is more friendly for the learning parity with noise assumption, as I said before. And how we can do this, instead of starting with OT, we start with correlated OT. And correlated OT is exactly the same. It looks very different now on the slide, but it's exactly the same, except that the sender chooses always like only one message, and the second message is a constant offset of this message. And then you can rewrite what Alice gets. It's not RBI as before, but it's RI plus either delta if BI is 1, or just RI if it's 0. And it was shown that if you have correlated OT and a correlation robust hash function, then you can get oblivious transfer. So it's actually all we need to show is how we can get this correlated OT. And now this correlated OT, this looks already like, if you look at the dark blue and the light blue vectors, like, or if you look, then this adds up to delta times BI, because the RI we're over F2, so the RI cancels out. So if you write it now as like you want many of this, so write it as vectors, then this adds up that the parties, like the light blue and the dark blue, add up to a secret sharing of delta times the vector B. And so in other words, this is actually subfield vector Oblivious linear evaluation, if you're familiar with it. If not, it's not necessary for the rest of the talk. And it's subfield because BI here is a choice bit, so it's either 0 or 1. And yes, so now that we have that, we can use what I told you before, because delta times B. So what we need is an efficient is a compression of delta times B, such that that adds up to the secret sharing. This is exactly what we need. And so what we can use is we can use the distributed point function, as I said before, to get a efficient compression K0 and K1 of the vector that is the delta here. So to answer the question before, the Y before is the delta here. This is something that is chosen and only known to the sender. And so if we have that, then we can repeat this many times via addition. And then, so this is just like, you just get many keys and then you evaluate all the keys and then you add it all up. And then with learning parity with noise, you get from something that is just a sparse vector, you get to pseudorandom vector. And here you basically use the linearity, so that delta times the matrix times the vector is the same as the matrix times delta times the vector. So this would, and it gets a bit smaller because we have this kind of shrinkage, if you remember the slide on the dual LPN assumption. So this is all like, this is actually all like what I said before. This is all the magic, where the magic comes from. And but now I want to go a bit into detail about the steps and how we actually do it. So first, I promised a two-round distributed setup. I said we can get two-round OT extension, and actually, as I wrote it, you cannot get a two-round OT extension, because distributed point functions, you can set them up very efficiently in a distributed way, but you need log n numbers of communication, where n is the length of the output. So this is certainly not true. But an observation that you can make here is that in the setting, the distributed point functions are actually kind of an overkill. Why is that? Because actually the receiver knows the vector B. So the vector B, the red like is the choice bit. So in particular, the receiver knows the point where the point function is not equal to 0. So the receiver knows exactly the non-zero positions. And then we can use a different primitive. We can use actually so-called puncturable pseudorandom function. And punctual pseudorandom functions are a special case of constrained pseudorandom functions that we've seen this week, for example, in Ritten's talk on Monday. And puncturable pseudorandom functions allow to puncture a key. So if you have the punctured key, you can learn the pseudorandom function on all points except for this point where it's punctured. And you can get like, there's results that you can get the constructions like just based on the GTM PRF construction. So if you just as a short reminder, there, like you can see the tree, and you go along the tree by taking either the left hand or the right hand output of a pseudorandom generator that's length doubling. And if I just give out, of course, if I give out the green key, you can learn everything. But if I give out instead the orange keys, then what you can learn is exactly what is orange and blue. So you can learn everything except for alpha. And the key size is lambda times the length of the tree, so log n. So in particular, again, like maybe as a reminder, because usually we want punctual pseudorandom functions to have exponential output. Here, like we have the output is n, it's the output that we want to compute. So this is something polynomial and like that. So we will actually always evaluate the complete pseudorandom function. And okay, so Yeah, I don't know, is there questions or there's things blinking?
Well, Zvika was just wondering what noise you can handle for the LPN.
Like how high or how low the noise has to be. Okay, so like for practical instantiation, we of course want very low noise, because like the noise is because you have to repeat it noise many times. So this is directly how much communication you will have. But you can go like anything that still gives you something that gives you something non-trivial in terms of stretch. So you can even like slightly yeah, I have to like anything, like you can go as far up as the noise that you want, but you of course like you want to stop somewhere to get something non-trivial. But like the construction itself is not depending on like how much noise you have. Certainly you can have larger noise than square root of n, and you still get something interesting. I hope this answers the question.
Yeah. Yeah.
Is there another question? Okay, so now that you have puncturable pseudorandom functions, you have already a PCG for unit vector by just giving, you just give Bob the key and you give Alice the punctured key, and also delta blinded by the value at the punctured function, and this hides delta because of the security of the puncturable pseudorandom function. And just by adding up, it will all add up to 0, except for this one point where it will add up to your value alpha. So you have correctness, where it will add up to delta. So you get exactly what you want. And now still the question is, of course, how can we set up k star and k? And this, like in particular, how can we get a 2-round setup? And the strategy is based on the protocol for distributed point functions of Derner and Chalat, but optimized to the setting of puncturable pseudorandom functions. And the idea is now the sender can choose. So the problem is like, maybe like you can say, why is it a problem? Why cannot just the sender choose k and then the sender send k star to Alice? But of course the sender cannot learn alpha, because if the sender would learn alpha, then he would learn kind of the noise, and then we wouldn't have security then he could learn the noise, and then he could learn the input choice of Alice. So we have to find a way so that Bob can obliviously give k star to Alice, and this can be done via OTs, because actually what Alice needs is exactly the values that are off the path alpha, so she can give this as an input, like choice inputs to an Oblivious transfer protocol. And Bob can just, like in the first level, it's easy, he just gives the right and the left leaves. And in the next level, this is from Derner-Chalat, he can give like the sum of the right leaves and the sum of the left leaves, and this is actually sufficient for Alice to compute what she needs. And what is special about this is that these OTs can be executed in parallel, because Alice knows the path from the beginning and Bob knows the key from the beginning, so there's nothing adaptive what you need for distributed point functions. And yes, and then like we said, like we need to get from unit to sparse vectors. You just add up. And you can even do something smarter. So you can, instead of adding up, you can choose smaller vectors and use concatenation. And then you need to assume learning parity with noise, learning parity with regular noise instead. So where you know, like you have the noise and you know, here's exactly one noise coordinate, here's one noise coordinate, here's one noise coordinate. But like this also for, this seems not like to be broken by similar attacks. So you can, you can also use this for more efficiency. And then the third part is the bringing in the learning parity with noise. So how can we get from sparse to pseudorandom vectors is just by multiplying this vector, the parity check matrix. And here is the main challenge, and this is something that I haven't like really said before. So the problem of our approach is that this parity check matrix is big. So it will be as large as the output size. So if you care about generating 10 million OTs, the dimension will be 10 million. And so what you can do is, for example, use quasi-cyclic codes to get multiplication n log n. So this makes it more practical. It's still slower though. So from a computational viewpoint, it's still slower than for example, IKMP, but I'll say more about this in a slide. And what you get for security is the security is similar, like if you use quasi-cyclic code, it's similar to post-quantum crypto system like BIG and HQC, but like just to stress here again, using this kind of assumption is only for concrete efficiency. If you just care about if you just care about feasibility or constructing something, you can use very conservative assumption. You can just use a random matrix, and you can use very high noise. So it's really a trade-off between security and efficiency. And yeah, to put it all together, this how does it look like? How does pseudorandom correlation generators for correlated OT look like? Well, Alice sets up alpha I, Bob sets up the keys, so I times, like each one for one of the noise vectors. So the more noise vectors we have, the more communication and computation is required, and also chooses the delta, sends ki star as described to Alice, and then they can expand it. So and then finally locally multiply the matrix. And just because of the linearity of the LPN assumption, the output will actually be give correlated pseudorandom OTs. And now going from correlated OT to chosen OT. So first one has to break the correlations. So you have to locally apply correlation robust hash function. Actually, we need something slightly stronger. We need a correlated input secure hash function because you get some extra information about short explanations of the inputs. But this is, so both are like, you can, like if you go to practice, you can use IS or something to instantiate this. And this gives you MPC with 2-round silent preprocessing. And then, as I promised also 2-round OT extension. If you talk about OT extension, like I talked only about random OTs, but of course, like in generally, you will also care about chosen OTs for like you like this, the receiver, like the receiver really chooses which messages she wants to get, and the sender really chooses which messages he wants to send. And now the question is, can we de-randomize also in 2 messages? And the answer is yes, because the sender can in any case send his de-randomization with the second message, and the de-randomization of Alice just depends on B, and B can be computed by her without any knowledge of anything of Bob. So it actually gives a 2-round OT extension, and it even can give with malicious security. In the Fiat-Shamir model, you can get a 2-round maliciously secure OT extension. If you don't want to go use Fiat-Shamir, you get a 4-round maliciously secure OT extension. And actually, like it's a slightly different assumption. You have to allow some leakage on the LPN, but this is also something that like intuitively doesn't give any attacks by just increasing the noise rate a bit. And so just as a comparison, what you will get is to generate 10 million random OTs. As I said, the problem or the bottleneck of our approach is the computation. So if you have a very fast connection and like slow computer, then you will have like you still want to use IKMP, but the more so as you can see here, IKMP goes from 0.2 seconds to something over 2 minutes. So it's very sensitive to the network connection speed. And this is something that like using PCGs with the silent OTs, with the silent feature, you don't have, as you can see, it almost doesn't change. It goes from 3.3 to 3.6 seconds. So you get really almost factor 50 improvements if communication is the bottleneck. And yes, so this was what I want to say for like OT and OT extension. Maybe are there any questions? And if not, I would continue to the second part.
Okay, the question, maybe you can read it. I don't understand the question.
Yes, so the question is, when you improve the DPF setup via puncturable PRGs, you still have to do this a logarithmic number of times. Why is it better than the before? So what is like, so it's not about, so we need to do it like, however, the noise rate is T many times, but this like, this can be like, this is, can be small, but the number of rounds, so it's really the number of rounds you need. So, and for DPFs, it's like how you set up the keys. So it's just about setting up K and K star, or the DPF keys K0 and K1. You need to this is an adaptive procedure. So to do it like once, you need really log n rounds. And now you only need 2 rounds with puncturable PRGs. And of course you have to repeat T times, but you can do it all in 2 rounds. You just do all the rounds in 2 times. This is completely independent thing. So is this like, this is just about bringing down the number of rounds. I hope this answers the question. Any other questions? No? Okay, then I'll continue with the second part. So how can we get oblivious linear evaluation from learning parity with noise first, and then how can we get something more efficient? And so oblivious linear evaluation is just a generalization of oblivious transfer to larger fields, FP. So instead of Alice choosing 0 or 1, so getting like one or the other message of Bob, she will get a linear evaluation of the function by Bob, so A, B plus C. And this is maybe something that's more used. If you have OEs, you can locally transform it into a multiplication triple. So into a triple such that Alice and Bob share, have an additive secret sharing of a product A times B, and also both have secret sharings of A and secret sharings of B. So A0, B0, and A, B0, and the same for Bob. And yeah, this can be used for secure computation over large fields. And again, like you already see the colors, so you already see maybe what's coming. Like we want to rewrite it to get like to be able to use the techniques. And how you can rewrite it, you can write it as A times B. So this is just the entry-wise product of A times B. Is secret shared between the parties, so is D minus C, and this is just rewriting the above. So now that we know this, like we can just basically do the same as before. We just have to find a good way to write it. So you can write it like as A times B transposed, and then just ignore everything that's not in the diagonal. Like what we really care about is on the diagonal. But now A times B transposed, you can again just use LPN to compress A and B. So you can replace A by something sparse, so like H times something sparse, and B by H times something sparse, and then like just plugging it in the equation you have, this is what it looks like. And now you can change the brackets, and what you get is H times sparse matrix times H transposed. And this is great because now we just have like the only thing we have to compress is the sparse matrix, and we know how to, like, we can just view the sparse matrix again as a point function, and we know how to compress it. Of course, we lose a bit. So now we have, so there's like 2 observations. So we lose a bit. We have now T squared coefficient. So this means now we really can only have noise square root of n, because if like below square root of n, if we would have more than square root of n, then this would get like trivial. Now it would not be a sparse vector anymore. But still, if we go to smaller noise, this still gives something interesting. And I think there was a question. Or is it the same question? I know, like maybe we can take it to the end.
Yeah, I don't think there's any question right now. You have 10 minutes.
Okay, thanks. I should be good. So yes, and the second problem, so this is one problem, but this seems somewhat inherent, but the second problem is also the dimension grows, so quadratic, and now the computational cost grows quadratic. So now we're at n squared log n squared, and so this is too much to be practical from from an efficiency viewpoint. Another question? No, maybe not. I'm just gonna wait until the end. It's not far. So what can we do? So what we can do is like we can write it in a different way. So instead of writing it as a matrix with a matrix left and right, we can also write it as a tensor product, and then like the matrix, which just consists of all the entry-wise row products of this matrix. So this is like quadratically big. And now like you can like maybe like now you can ask like, why would you do this? Because actually this made things worse, because now we don't have structure. So now the straightforward computation time would be n⁴, or like whatever you need to multiply n² matrices. Yeah, n⁴. And now, but the observation, like the first observation is why is this interesting. This generalizes to more dimensions. So you can do like, you can get this for arbitrary constant degree. So this is like theoretically, this is interesting. And now you can also optimize that. So you can get a better efficiency by choosing H such that this long matrix H is compressible. And compressible in what sense? So compressible in the sense that only few of these rows are distinct, row products are distinct. So that you kind of like a lot of them are the same, and so you can just compress the matrix down and compress the tensor product down, and then have something that's more efficient. And like one way to do it is via using ring learning parity with noise. And so now this first looks very different, but the idea is instead of like for ring learning with errors, instead of using matrix times vector, you have polynomial multiplication. So you have a public matrix A, a public polynomial A, and you have sparse. So sparse in like meaning sparse coefficients S of x and E of x. And an assumption is that this looks close to E of x over set px mod phi of x for some polynomial phi. And yes, so this looks more like now more like the. So maybe like first intuition, why does this give something better? Because now basically instead of tensor product, you have a polynomial multiplication. So instead of going from n to n², so you go from n to 2n. So this is much better. And you can actually also put it in the picture that I have before, because if phi fully splits over set p, then you can write it as like going from the coefficient representation to the evaluation representation. You can use the van der Waals matrix, just consisting of all the corresponding to all the evaluations of series of phi, and A is just like writing it like this. A just corresponds to the matrix representation of A of the polynomial A. So this of course depends on how phi looks like. And actually, like, why does this give such a nice matrix as we had before? It turns out that if phi fully splits, then you can rewrite a V as V times just a diagonal matrix. So this is basically just a scaled van der Waals matrix, and van der Waals matrices have this nice property that I mean, it just corresponds to, like, it's just the same why you have this for polynomials, and then you only have like a linear growth. So you only go from n to 3n. So you need sx times sx², sx times ex, and like and the cross terms. And yes, so this actually gives us, it's just wanted to show also in the matrix representation, and this gives now n all e's over set p in O tilde of n computation time. Of course, now you have to assume a ring-LPN, like a arithmetic version of ring-LPN. So obviously this only works over big fields that phi fully splits. And you have to assume that even if it splits, like, you have security. So there's some attacks that you can take care of, and we did the analysis, and we believe it's secure. But this is certainly something that we hope more people will look into. And regarding efficiency, so like recently, like to get all e's, you could use, for example, overdrive of Keller et al. But there you have really, like, the problem is really the communication. So you have more than a gigabyte of communication, even for just 1 million OLEs, which is about 32 megabytes. And you could get something. This was like, I don't know if anyone saw the small green star. You can get something interesting even from learning with errors. and together with the MQ assumption for very like low degree pseudorandom generator. But this only gives you something. This is actually gives you some reasonable efficiency, but only if you start with a very large seed, because basically, yeah, just because LWE ciphertexts are very big, so you have to start with 3 GB seeds to even get any expansion. And but then like you get like much less communication, 6 GB, but it gives you 3 GB and not just 32 MB. But with this new approach, you actually get, even for just 1 million OTs, you get down to 7, like approximately. This is very estimated, but just to give you like an order of magnitude, you get like even less communication, that the amount of triples you want, and as a reasonable efficiency. And the efficiency again should be taken with some care, because you need extra time for setting up the seed. So this is just the expansion time, so just the silent preprocessing time. But like for example, in particular for the last one there, you can actually reuse OLEs. So you need a lot of OLEs. So you have a like expensive setup cost once, and then like from then you can reuse the OLEs if you want to redo the setup. So this is a nice property. And further, we also get malicious security, basically making the distributed point functions set up from Durner and Shalat, making it maliciously secure, and it generalizes to authenticated multiplication triples at very low cost. This is like a nice property also about the linearity of learning parity with noise, that going from triples to authenticated triples is almost for free. So it's not, even though it's like a degree 3 correlation, it does not cost you like how like a degree correlation would cost you. And yes, so this was just like a short excursion to give some ideas of this work. And to conclude this talk, yeah, I talked about PCGs for oblivious transfer from learning parity with noise. I mean, I mostly talked about why learning parity with noise and is nice for pseudorandom correlation generators. So you get, for random OT, you get something practical, almost zero communication. We have a 2-round OT extension with malicious security, also have an implementation. And for we showed like very recently that for oblivious linear iteration, you can get a more efficient instantiation based on fully splittable ring-LPN. And there's a lot of work still to do in this area, as it's a very like young area. So one thing I kind of already mentioned is to optimize oblivious transfer, so find better codes. Like quasi-linear is something, I mean, the difficulty is of course to find something that is like, it's efficient to evaluate, take h times this error, that should be efficient, but learning parity with noise should be has to be hard, like otherwise of course we don't have security. In like generally, can we extend the techniques? Now we extend it to OLEs to get something efficient. Can we get and multiplication triples? Can we get it for more correlations and like a better understanding? So we use a lot of like kind of new flavors of LPN assumptions. Like, can we get a better understanding of the security? Can we relate it to other known things? Yeah, other attacks. So this is yeah, lots of things to do. And with this, I want to conclude my talk. Thanks, yeah, very much for your attention, and again for the invitation to the workshop.
Okay, so.
And I think there's a bit of time for question. I don't know.
Yeah, there's a little bit of time for questions, so maybe we can take a few if people have. So can you see the Q&A? Maybe you can.
Yes. So maybe for some applications correlations, you can do the same from LWE. So this is actually like a very interesting question. So as I said, like what we have from LWE is like using LWE to construct a homomorphic secret sharing scheme, and then use like a very low degree, like a degree 2 pseudorandom correlation generator. Of course, a different direction would be using LWE the way we use learning parity with noise, but we don't know of any efficient way to compress this noise. So it's not clear. It seems really that LPN seems to give something more efficient for like, yeah, for all things we know. But certainly like to extend the techniques and to look in what can be done for LW is an interesting problem. Other questions? In the PCG for, okay, so the next question is in the PCG for OT from learning parity with noise, how does one of the parties get the value PRFK of alpha plus delta into rounds? So this is something that for OT, it's actually very quite simple, because the sender can just send it, because the sender knows he can evaluate the pseudo-random. Oh no, okay, no, this is of course wrong, because he doesn't know where alpha is. So you do the same trick as you do before, and you sum up all the leaves. So you sum up, like you just sum up all the leaves of the GGM tree. You sum up all the leaves, and then you add delta. And because the other party can compute all the leaves except for the one leaf, the other party can get all the leaves, can exactly get this value plus delta. But this is something that the sender can just send along. So this is just with the second OT message, just send this along.
Okay, great. So let's take any remaining questions offline, and let's do let's reconvene in 9 minutes, let's say, for Nico's talk. So Pacific time, that would be 9:45. Okay, and let's thank Lisa again, although I guess I'm
Thank you.